All right, guys, this lesson builds on what we started for our trig review last semester. We're still in chapter 4 in our textbook. This, we're going to talk about a few things today that tie into exactly what we did. Like we're going to talk about converting degrees to radians and all that kind of stuff. We did some of that already, okay? But today's lesson primarily talks about breaking angles down, and about angular and linear velocity are the big things. All right, this is all review. Is there anything on this screen that somebody doesn't know the meaning of? Initial side, terminal side. Okay? Everything in trig starts off the positive x-axis as your initial side. And if we're rotating counterclockwise, it's a positive angle. If we were to choose to rotate this way, it's a negative angle. Not new, right? We all know that? Okay, the only exception to this is going to be eventually we're going to do bearings questions where you measure off of north and go in a clockwise direction. Yeah, I know. Those of you who have trig, you just had a little baby barf maybe, or they're not the most fun questions. Okay. All right, this talks about converting between degrees, minutes, and seconds, or breaking degrees down further and further. My initial reaction when I think about these kind of questions is, who cares? Because when I think about it, a degree is already so tiny to me because I'm used to looking at my protractor, something I draw on my paper. So a degree is really little, right? Like if I ask you to measure, is this a 39 or 40 degree angle? You're all going to go, yeah, it's either 39 or 40, right? But if you're talking about on the surface of the earth, 1 degree, if you took the earth and you put a giant protractor on it, 1 degree along the surface of the earth could be thousands of miles, right? That's why latitude and longitude is broken down into tiny little degrees, minutes, and seconds. Okay? Now the difference between whether it's a decimal or it's degrees, minutes, and seconds, it's kind of up in the air which one we need. I will tell you this. We're going to talk about converting today. The calculator does it. I'm going to show you how the calculator does it. And I will be honest and say I have not written the first quiz yet. So I don't know if this is something I'm going to put on the first quiz or not. But pay attention because I promise if it's on the first quiz and you go, I don't remember how to do this, I'm not going to tell you. Okay? If it's on the first quiz, you need to know how to do it without me showing you on the calculator again, so pay attention. All right. A degree is broken down into 60 minutes, and each minute is broken down into 60 seconds. Does that sound like time? Okay. It's just like hours. Hours, minutes, seconds, degrees, minutes, seconds. Okay. It's based on the base 60. All right. We're going to talk about these 2 examples down here at the bottom. They are at the top of your worksheet, okay? To practice this. Before I start, how many seconds, let's just say in an hour? 3,600. Everybody get where that comes from? 1 hour is 60 minutes, and every one of those minutes is 60 seconds, yes? So 60 times 60. We good? The same is true of a degree. How many seconds in a degree then? 3,600. Okay? This is a decimal answer, and we want to change it into degrees, minutes, and seconds. The symbols, degrees, little circle. Minutes, single apostrophe. Seconds, double like quotes. Okay? I'm going to do it by hand, and then I'll show you on the calculator. To do this by hand, you would say, how many whole degrees is this? How many holes are there? 213. What's the part? There's another 0.875 of a degree, right? How do I change that to minutes? I'm going to use my dimensional analysis because that's what we're going to use the rest of the day. every one of those degrees is how many minutes? 60 minutes. So if I multiply 0.875 times 60, what do I get? Need a calculator. 0.875 times 60, 52.5. Now what's the label on that? Minutes. When we did our dimensional analysis, we got rid of the degrees. We're down to minutes. Okay? How many whole minutes is that? 52 minutes. And what part? 0.5 of a minute, which most of you could do without the dimensional analysis. 60 seconds in 1 minute. So 0.5 times 60 is 30 seconds, or 30 with a little apostrophe. So this is 213 degrees, 52 minutes, and 30 seconds. In this particular kind of a problem, the calculator is your friend. Okay? This is a big pain in the neck that the calculator can do like that. The second one, I don't like using the calculator for, but this one, use calculator. What you're going to do, the only thing you really need to remember about this, guys, is that there's an angle menu on your calculator. Can you find the angle menu? It's by the apps key. Okay, so what I want you to do, let me pull this up so Faisal will be able to see it. Come on, my dear little Webbit. There we go. What we want to do is just type the whole decimal on the screen, 213.875, and then find that angle menu, which is second, and then the apps key. And what are we trying to change this into? Degrees, minutes, and seconds, which is choice number 4. That little arrow there, that little triangle that's sideways, means into degrees, minutes, and seconds. So go down or type number 4. Hit enter, and it gives you 213 degrees, 52 minutes, and 30 seconds. Are we good? So I probably would never bother to do one of those by hand. Okay. On the other hand, this next one is more painful on the calculator, in my opinion. The basic idea is that this is 89 degrees plus 56 what? Okay, so 56 60ths of a degree, yes? Plus, you tell me again, how many seconds are there in a degree? 3,600. So this is how I would do this question. I would say those 56 minutes are 56 60ths of a degree, and those 7 seconds are 7 3600ths of a degree. I would type it like that, because I'll show you the other way to do it, and it's a pain in the neck. So 89 plus 56 60ths plus 7 3600ths is 89.93527, repeating, I think. Okay? We could round at some point, but that's the decimal we're looking for. Now, to do this without prior knowledge of what those equivalencies are, you would have to type in this on your calculator. You ready to try this? You would type 89. Ready doing this? Go to the angle menu, second apps, put the little degree symbol. Now type 56. Go back to the angle menu, second apps. Go down to number 2, the little apostrophe. Then type 7. Okay, what happens if I go back to the little angle menu? There's not one there. Okay, that's because it's already on your home screen. Okay, anybody find it? Yes, it is down here by the plus sign. Do you see the quotes? They're green, so you have to do alpha and then the plus. Now you have 89 degrees, 56 minutes, and 7 seconds. You just hit enter. It changes it back to the decimal. I find that a huge pain in my neck. Okay? if I were to put one of those on the quiz, you either need to know how to do it by hand or on the calculator. We good? Okay. Very basic concepts, changing back and forth. All right. Talk about degrees and radians now. Angles and degrees are appropriate in a lot of trig application problems. Okay? Unfortunately, when angles are measured in degrees, pose a problem when we want to relate it to a linear measure, a distance. Okay? Such as if you want to take inches times degrees, there's no such label. Or inches per degree. Okay? It doesn't exist. It has no meaning. That's why they developed the idea of radians, and we're going to talk about where that came from real quick. And I don't think Faisal will be able to see this. Let me see what happens when I do this. I know he's going to be stuck watching that. Okay, I'm going to pause this. Nothing didn't go off. Okay, hang on. Recording again. All right, so the definition of a radian is a central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. So when S and R here are equal, okay, it's that amount of turn is a radian. Now, this gray sheet you received today is your reference sheet for this semester. You're going to have a few other reference sheets we use on and off. There are 3 possibilities for this reference sheet in terms of tests and quizzes. There are some for which you will be able to use it not at all. There are some for which you will be able to use it free of charge. And there are some for which you will be able to use it at a fee. In other words, if you need to use this, it's going to cost you 5 points on the test or something. Okay? Now, the first, and I will tell you every time before an upcoming quiz whether you get to use the reference sheet. The first quiz is this Friday, and the quiz is on whether you have the unit circle memorized. Guess what? You can't use the sheet at all, okay? But for today, we're going to talk about some formulas relating angular and linear velocity and arc length as well. And I just want to want you to know where those are. Where are they on this sheet? Do you see this formula anywhere, this theta SR or S times R equals theta? Anything? It's on the side that has the unit circle right up at the top. Do you see them up there? Everybody see what I'm talking about? Okay. I just want to make sure you identify where that is on there. All right. Notice that as long as the arc length and the radius are the same, if you take an arc length of 6 inches and you divide it by a radius of 6 inches, 6 inches divided by 6 inches becomes 1 with no label. The inches would cancel out. That's why we usually talk about radians as these magical units that appear and disappear. Okay? The word radian is often omitted when writing the radian measure of an angle. So if you see a plain old number 2.5 and it's talking about an angle, it says theta equals 2.5, it's radians, even if there's not a pi. We always think it's got to be a pi, right? In terms of pi. All right. You know this already, right? I can skip this slide to convert radians to degrees, degrees to radians. We're good. Positive coterminal, we already talked about that. Okay, except for coterminal means you add what? Remind me. 360 degrees. What, can I subtract 360? Okay. Anybody remember what the positive and negative whole numbers are called when we combine the positives and the negatives? What? The set of numbers. When you say all the whole numbers and the ones that can be positive or negative. Integers. Somebody said it. They are the integers, okay? If we want to talk about every multiple of 360, that's a whole multiple of 360, we're going to say when n is an integer, in other words, a positive or negative whole number, we're going to take our reference angle and add or subtract 360 times that integer if we're in degrees. to find all the coterminal angles. Your book only uses plus because integers can be negative. So when I write plus 360n, it can be negative. I don't care if you write plus or minus. I learned it to write plus or minus, and it helps me remember that it could go either way. I could be adding or subtracting. So I will always write plus or minus. Okay? That is the way to write all angles coterminal. Why would we ever need to do that? Well, we're going to spend a lot of time this semester answering questions like this. Where is the cosine exactly 1? This is not about today's lesson, but do you remember that the cosine does this? That we're going to hit that this week, okay? But do you remember that it hits the value of 1 as its maximum every 2 pi, yes? Its period is 2 pi. If we're in radians. If we're in degrees, its period is what? 360. So the solution to this is actually an infinite number of answers, yes? Where does the cosine hit 1? Well, it hits it at 0, it hits it at 2 pi, it hits it at 4 pi, it hits it at 6 pi, it hits it at 8 pi. Do you get the idea? Negative 2 pi, negative 4 pi. So when we start doing this, we're going to have to be able to write this is 0 degrees plus or minus 360n. Or we're going to say 0 radians plus or minus what? 2 pi n. All right, so I'm trying to show you why we're going to need this, and then think about what this means. Now, could I have said 2 pi plus or minus 2 pi n? Let's do it in degrees. It's easier for us to think about. If I write negative 50, what's another name for that? Okay, so that's also 310 degrees. Are those equivalent? Negative 50 add or subtract 360, 310 add or subtract 360, etc. They're the same thing. Okay, I just added another 360. There are infinite answers for this kind of equation. We're going to pick the easiest one we can come up with, and then we're going to say plus or minus either 360 or 2 pi, depending for degrees or radians. All right, so these two questions, right? These 3 questions are on your worksheet, yes? Okay, so we're going to write, how do you identify all coterminal angles? Well, you write negative pi over 2, and then you write what? Plus or minus 2 pi n. Why not 360? Because this is radians. Now, if I was a really mean witch, I would say you have to write where n is any integer next to every one of those. I'm not ever going to make you write it, but you need to know it and understand it. Okay, so every multiple of 360 or every multiple of 2 pi can be added onto this. What's number 3? 135 plus or minus 360n. Notice I didn't put a label on this one, but I did on this one. I made sure it said degrees, either one or both places, right? Remember, you don't need a label when it's radians. And the last one, 5 pi over 3, 2 pi n. Okay? Now, we're going to have equations eventually that don't have 2 pi as the period, and then we're going to have to put like plus or minus pi over 2n and all kinds of weird stuff, okay? All right. I felt like there was something I forgot to talk about back here. Oh, yes, the Greek letters. If I talk about, we'll say 310 degrees, we're going to talk more about reference angles tomorrow, I think, but 310 is around here with a 50-degree reference angle. Everybody know what I'm talking about? Degree to the x-axis. Your book calls this theta, and they call this theta prime. When I learned it, I learned this is theta, and I know the old trig book does this. It calls alpha the reference angle. It doesn't matter. It's a reference angle, whatever you want to call it, okay? But I just wanted to review with you. There are here real quick three of the Greek letters they use a lot are alpha, beta, and theta. Everybody know those? I don't care how you write them or what. There's also, we're going to talk today about these two. Okay, this is a lowercase omega. I'm kind of confused on this one. I think it's a upsilon. Our book, luckily, just calls this V, capital V. But I think it's when I wrote it here, I wrote it as upsilon. That's what the old book uses. All right, here we go. We talked about this. S equals R times theta. Okay. So arc length, you have this on your notes. The distance we get around here in radians. The theta has to be in radians, and we multiply by the radius, and we'll get the arc length. You have that formula on there. Okay. The rate at which an object moves along a circular path is called the linear speed. That's how fast something moves along here in centimeters per second, miles per hour, whatever, okay? If you think about this for a second, visualize in your head, you take your bicycle out, it's spring, okay? Take your bicycle out, and you take a big chunk of chalk and you mark a spot on your tire. And then you drive down the street on your bike, ride down the street. And then you take out your tape measure and you measure that distance. Every time you went around once, you're going to get another mark on the street, right? If you measure how fast you went in miles per hour or feet per second, how many marks you made down the street, okay, that's a linear velocity. It's how fast that little mark was going around the outside and tracing out a line. Make sense? The angular velocity is how many times it was turning per time. The easiest way to think of angular velocity, though it's not a true definition we're going to talk about, is how many times did it turn per minute, like revolutions per minute, yes? Okay. So in order for me to ride my bike that far, how many times did my bike wheel have to turn? Okay, but that in our definition for pre-calculus has to be in radians per time. So we have the pace at which it moves around the outside of the circular path is its linear speed, and that's got to be in distance per time. Okay, and the rate at which the object rotates around a fixed point. The fixed point is the center, right? The rate at which it rotates is called the angular speed, and that must be in radians per time. You have this little chart on your notes, yes? So what we just said is that linear speed, which your book uses as V, I will usually write like this because that's the way the trig book uses it, has to be measured in distance per time. Now, that's really not a label. Those are the kind of units. What are some actual labels that could be? Okay, miles per hour or mph. What else? Feet per second. What else? Meters per minute. Would that work? Okay, etc. Get the idea? It is a distance divided by a time. If the angle is in radians, then it is called an angular speed, and they use this little omega, okay, to say angular speed is radians per time. So it has to be radians per time. So that might be radians per second, might be radians per hour, etc., radians per minute. Okay, what it is not is RPMs. What does RPM stand for? Okay, revolutions. If you said rotation, I wouldn't say it's wrong. Revolutions per minute. So what if I told you something was rotating 100 revolutions per minute? How do I change that to an angular velocity? You know that. You can convert that to an angular velocity. To be an angular speed, it has to be in radians. So all you need to do is change revolutions to radians. How do you do that? One revolution is 2 pi radians. Using my dimensional analysis, revolutions cancel. I have radians per minute. I get 200 pi radians per minute. Now it's an angular velocity. Here, when we started out and it was in RPMs, was not an angular velocity. Everybody good with the difference? It's got to be in radians per time to be an angular velocity. I like to call this its cousin, okay? RPMs is kind of, they're giving you the angular speed, but it's not quite an angular speed yet until we change it to radians. All right, I'm going to go through this example. I would like you to help me, but you can just not write it down because it's already done for you, yes? Okay, real quick. Find the angular speed and the linear speed. If 8.2 revolutions are completed in 3 seconds. Okay, I have revolutions per second. What is that? Is that an angular, linear, or neither? It is neither at this point. What is it close to? It's close to an angular, but I need it to be in what? Radians. So what can I do with that? One revolution is 2 pi radians. Multiplying or dividing? Multiplying by that 2 pi, right? Dividing by this 3 over here. The labels I'll have left is radians per second. Is that okay for an angular velocity? Okay. So 8.2 times 2 pi divided by 3. Can you type that in? Everybody knows where the pi key is? Divided by 3. I wrote times. 17.17. Somebody getting that? That's your angular velocity, the angular speed right here, okay? The linear speed, we need a distance, right? To be a linear speed, v, we need a distance. Do we have a distance so far? I don't have any kind of distance, but did we read the whole question? The distance from the center of rotation is 7 centimeters. What in the world does that mean? The distance from the center of rotation? It is the radius, okay? The radius is 7 centimeters. What are we going to do with that if we want distance divided by time? We have 17.17 radians per second. What do we need to do? Jacob? Thank you so much. What else? I also have seconds here and I want it in minutes, so we can do some converting there. 60 seconds is a minute. Got to multiply by 60. But what else did it say I wanted? It says I wanted distance per time. I have radians per time. Remember the whole magic of radians? They can what? Disappear. So what could we do to replace that with a distance up here? Multiply it by that 7 centimeter radius. This will just go away and we'll have left what? Centimeters per minute. This is also known as this formula. Do you see that on the reference sheet? Look for me. Where is it? Top right hand corner of the side that has the unit circle, right? Okay. We just did angular times radius equals linear. All right, so it would be 17.17 times 60 divided by times 7. I don't know why I can't type that in right. What did I do wrong? Do they want it in... What is your answer on your page? 120.2. Oh, they left it in seconds. That was really nice of me to change it to minutes, but your paper didn't change it to minutes. Okay. So what they did is they left this out, and they just did that times 7. And 17.17 times 7 is the 120.2 centimeters per second. All right, I don't know why I changed it to minutes. I just randomly decided we should change it to minutes. I think because here, look, it talks about minutes on these. Anyway, okay. We don't have a lot of time. I'd like to get through a couple of these real quick. This section of the notes, okay, first of all, we will pick up with what we don't get done tomorrow. You are ready to start on page 238 in the book? Okay. Page 238 in the book, which is, I think, written at the actual problem numbers are on the bottom of 2A, yes, which we will get to by tomorrow. But for today, I'm going to start with a couple of these. I don't know why, but they in this section on the notes and in the book, they lumped two different kinds of questions together and made the directions really confusing. It says, find the rotation in revolutions per minute given the angular speed. And then it says, or means, and find the radius if you're given the linear speed and the rate of rotation. So these two problems, or the next three problems, you're given a angular speed that they want you to change to revolutions per minute, okay? Then starting with number 8, you are to find the radius because you're given the linear speed and the rate of rotation. I don't know why they just made it really confusing. Okay, let's get at least one of these done. 2.7 radians per second. How do we change that to revolutions per minute? Somebody give me a conversion. 60 seconds is a minute. We want revolutions. 2 pi radians is a revolution. How does that go, though? I need the 2 pi radians to cancel because they want me to have revolutions. You will get this wrong every time when you divide by that 2 pi unless you put it in parentheses. Because if I type divided by 2 times pi, it's only going to divide by the 2, and then it's going to multiply by the pi, right? If you want to divide by both the 2 and the pi, you need parentheses. All right, so type 2.7 times 60 divided by parenthesis 2 pi. The seconds cancel, the radians cancel, and we end up with what? 25.78 revolutions per minute, or you can just write RPMs. Number 6 is kind of a pain in the neck because the answer comes out real weird. It's almost easier to do some of this in your head or on your paper. We want revolutions per minute, so hours to minutes. What do I need? 1 on the top, 60 minutes on the bottom. I don't know. Oh yeah, that's 4 pi over 3. That's what they started us with. Okay. And I need the whole revolution to radians thing, right? All right. This would be easier to do some of this ahead of time. 2 pi on top, on the bottom, 4 pi on the top. What could we do? Yeah, this is just going to be 2. So what's left is we have 2 times 1 times 1 on the top and 3 times 60 or 180 in the bottom, which is 1/90th or 0.01. Yeah, repeating, disgusting, revolutions per minute. Is that fast or slow for most of us to think about? 1/90th of a rotation per minute or revolution per minute. That's pretty darn slow, right? Then again, if it was the Earth, we'd get a headache. It'd be so fast, right? Because it doesn't rotate that fast. All right, so we will pick up with this next slide tomorrow. And the assignment you should get started on is here.